All right, guys, I want to pick up where we left off yesterday. All right, so starting with this one, what we're going to do today is maybe do a handful of examples and then show you why the procedures that we're going through actually work. Okay? So with x squared equals 5x plus 100, what do we have to do first here? Any suggestions?
Factor in 5, and distribute it.
Okay, so we get x squared equals 5x plus 500, right?
Yep.
Okay, then the next thing I want to do is move everything over, right?
Yep.
So x squared minus 5x minus 500 equal to 0. All right, so 500 is a pretty large composite number, right? So here's the thing. I don't like to just sit and try random factors. Does that make sense? Because that's like throwing a dart at a dartboard with your eyes closed, right? Okay. If I'm throwing darts, it's going to be easier just to walk up to the dartboard and just push the dart into the bullseye. Okay. So that's kind of what I want to do. I want to have a structured method for finding these factors quickly. All right, so what I do is when I see that C term is a very large composite number, I then look at the B term, okay? And I look at the size of that B term, and the size of that B term is relatively small, right? Okay? I don't really care that it's positive or negative, I just want to look at its size, okay? 5 is not too bad, okay? What that tells me then is that if, let's just assume B was 0. If B was 0, then one of the two factors that multiply together to give me 500 has to be 100% opposite values. Okay? And if I have two numbers that multiply together to give me 500, and they were opposite values to add to 0, doesn't that mean, by definition, that those two numbers would have to be the square root of 500? Okay. But since 5 is relatively close to 0, that must mean the factors for 500 that I'm using are relatively close to the square root of 500. Does that make sense? Okay. So the way that I'm going to generate these factors or find them quickly, instead of making a list or just kind of trying to develop the factors randomly, I'm going to take my calculator. I'm going to take 500. And I'll take the square root of it. Okay? So a lot of times when we take square root on my calculator, I'm going to use the 1/2 power. Okay? Same thing. I think it's easier to type in. So 22.3. So that's what I would use. I would use a positive version of that and a negative version of that if my B term was 0. But my B term isn't 0, so I need to kind of move away from 22. I need to either increase or decrease from 22. And it doesn't matter because one of your factors is going to be above 22, one's going to be below it. Does that make sense? So it doesn't matter the direction you go. I'm going to then take 500, and I always go up, so I'm going to just divide by 23. I'm looking for, remember, integer factors. So 23 and 21.739 are not integer factors, so 23 doesn't work. So then I'm going to go to the next integer. That doesn't work. So then I go to the next integer, 25, and I get an integer result. Does that make sense? And every time I do that, that first integer result paired with the divisor of 25 will end up giving me my other factor. Okay? So 25 and 20. Now that's, my hopes are something that we maybe saw in this one already. 500, 25 and 20, because 50 is 25 and 2, right? So I was hoping that maybe we see that, but it gives us a procedure for those maybe more difficult problems where we can't see the factors that easily. So it's going to go to x. Now I've got 25 and 20. Which one's got to be positive? Which one's got to be negative?
Negative 25.
Negative 25. So then that's going to eventually generate x equals 25 and x equals negative 20. Okay? So my thought pattern here, guys, and you're going to see a couple more examples like this where we do them two ways. If this is on a test and you're sitting there and you're burning time because you can't think of the factors, okay, or that you write down two factors and then write down two more and then write down two more, you make that list that maybe you learned in Algebra 1, you're going to waste time on that test. Okay? And the tests are designed for you to be able to finish them in the time period that you're given, provided that you use the most efficient routes on those specific questions. Okay? You know, if each question has 3 routes and you choose the slowest route on each question, you're going to be here all day, you're not going to finish that test. Okay? So kind of keep that stuff in mind. That's a technique that's going to help you speed things along a little bit with those types of questions. All right. Before we go on to the next idea, I want to talk about, I told you yesterday that I was interested in you guys being able to see why some of the things that we do work. Okay, why does the AC method work? Why does the product sum technique work? Okay, I'm going to start with the product sum technique. Maybe on Monday we'll do the AC technique. It's not that much different. Let's start with this. We're going to do a proof here. Okay, so this will be a proof of the product sum technique for factoring. Okay, so first thing I'm going to write here is assume that x squared plus bx plus c is factorable across the real numbers. I would. And that b and c are elements of the real numbers. So all I'm saying there is I've got this quadratic, okay, or we got this trinomial, and I know it's factorable, okay? And basically when I say it's factorable across the real numbers, all I'm saying is that when I'm done, these factors are going to be real numbers, okay? And I know that B and C were also real numbers, okay? So basically I'm just eliminating any potential for I to show up in any of this stuff, okay? If I assume that, and I know that it's factorable, then basically by the definition of multiplication, factors, and products, we should know that
What's that thing for the real number?
that little E stands for element of. Okay, so if it's a trinomial and it's factorable, we know it should factor to x plus something times x plus something, right? Does that make sense? Okay. Now those somethings, I'm going to make them arbitrary. I'm going to make them m and n. You can use any letters you want. A lot of times when you see a proof like this, they might use p and q. But x squared plus bx plus c, that's what we started with. We know it's factorable, so we know it will break down to x plus m times x plus n. Okay? and I'm just going to say where M and N, whenever I bring in new components, new arbitrary values, I'm going to tell you where they come from. I'm going to say that they're real numbers, okay? We're going to write, therefore, we know that, you guys agree that x squared plus bx plus c, just taking the left-hand side of this, would also equal, if I take the right-hand side of that and FOIL that, so that right-hand side FOIL to that, does that make sense? And those two things should be equal, right? We say we start with x squared plus bx plus c. We know it factors down to two factors, and we're going to call them x plus m and x plus n. And we know that if we factor something, we can always undo that factoring through multiplication, right? So I'm going to multiply out that right-hand side, and I get x squared plus mx plus nx plus mn. Now, I'm also going to, so I'm going to rewrite this left-hand side, and I'm going to take the right-hand side, and I'm going to do this. Oh. Does that make sense? All I did there was I took these two terms. Don't those two terms both have an x in them? So I factored the x out, and I'm left with the sum of m and n, right? Okay? Now let's make the link. Basically, now we're done. We're done with the algebra for this proof. Now we just have to make the association that allows us to kind of develop the link between the product and the sum. If I look at that term right there, these two things are equal, right? So shouldn't C equal that? So I'm going to write, therefore, C is equal to M times N, and B, that term right there, shouldn't that relate to that? Okay, so now we have shown the relationship that when we look at ax squared plus bx plus c, if we want to factor that, okay, we're going to be looking for c, we're looking for factors m and n that multiply together to give me c, but m and n are going to add to give me b. Does that make sense? Okay, so that's the algebra that we're looking at. Now, when we're done with the proof, okay, we put that little, sometimes you got an option here. Sometimes you put that little box down there and shade it in. I forget the guy it's named after, but they call it his tombstone. It's a guy that was doing like proofs in like the early 1900s. He just introduced that in his proofs, and other people started using it, and it's just what we do. Okay. Now the QED that you write at the end of a proof is Latin. I don't exactly remember the phrase that it is in Latin, and if I did, I probably couldn't pronounce it anyway. But it essentially says what we've been asked to show, we have done that, okay? Or what we set out to prove has been completed, okay? But that, guys, that's the kind of algebra that we are kind of working our way towards, all right? You go to college, so college math, I don't know, I don't want to scare anybody, but college math, I would say of the, I don't know how many math, I took so many math courses, but I'd say more than 2/3 of them focus on things like that, or incorporate things like that, or have prerequisites that said you have to have taken a course with heavy proofs, or heavy proof work in it, okay? All my graduate classes I took in math, I had to have prerequisite kind of analysis classes to show that I've got that proof background and I'm going to be successful in those courses. But that's kind of that's algebra. Does that make sense? The algebra that we do, yes, it's algebra, but we're doing specific problems. Right there, I have shown that I can now factor every single problem, okay, using that specific technique, or every problem that is set up to use that specific technique. You cool with that? Okay. Now, I'm not going to ask you early on to maybe produce something like that on a test or a quiz, but I want us to start transforming the way we think about mathematics as, kind of a monkey see, monkey do, always working with numbers, that type of thing, okay, where we start doing the mathematics with all numbers at once. And that's basically what we did here. Every, M, N, A, B, C, those are standing in for any values that we want. All right? Okay. We'll do one more of those here towards the end. Hopefully the one we do at the end you've maybe already seen once before. Now, so I'll get to the square root method. Okay, the square root method, there's a couple different things you can do here. Some people totally ignore the square root method. And I think if you ignore it, you are, I don't want to say stupid, but you're doing a disservice to yourself. Okay? Because the square root method is the easiest technique to do any factoring. Okay? And all you have to do to use the square root technique, we talked about this yesterday when we developed that hierarchy of factoring procedures. The square root property or technique only works if B is what? B is 0. Okay? Otherwise, you can't take square roots of the expressions that you're left with. So, when I want to take square root or square root method, and I've got something like this, B is obviously 0, all I have to do is what everybody wants to do anyways, is isolate that. Okay? I'm going to isolate that. And what I mean by what everybody wants to do, I will get a lot of people when I have like a x squared plus 5x minus 4. They will isolate the x squared and take the square root of both sides. You can't do that because the b term is not 0, but that's what they want to do. Instinctually, we want to undo the x squared right away, so we do square roots. This is the time that you can actually do that. Okay? So now you take square root, right? X is equal to 2. Now, when I write x is equal to 2, am I right, Chuck? Why am I wrong? Okay, good. So we'll take square root, guys. Remember, it's always plus or minus. Okay, that's something that, just because of the course we've taken in the past, maybe we start to neglect the minus. Remember, in geometry, we were always talking about taking square roots with distances, right? Mm-hmm. And we started getting just kind of avoiding the negative portion, and we train ourselves just look at the positive ones, and then we get to a class where we have to have both of them, we forget. Okay, so make sure that you're doing that, keeping both versions. All right, anybody want to do that a different way, or did anybody think about doing that a different way? If I look at x squared, put a number in for x. Any number you want to. What does that number kind of turn into? What vocabulary word does that number turn into? If I put 7 there, it turns into 49.
7's my favorite number.
Is it?
It is.
Wow. What if I put 5 there? What's that turn into? 25. What if I put 6 there? 36. What are those numbers? Perfect squares. What's 4? Perfect square. What's another word for subtraction? Starts with a D. Ends with difference. Difference, right?
You said division.
So,
Oh, I heard you say division.
So, when we look at that, we've got a difference in perfect squares, right? Did anybody think about taking that and rewriting it as x plus 2 times x minus 2? Okay, and that's fine. I don't know if that's any faster or slower than doing the square root method. Okay? So that will eventually lead me to x equals plus or minus 2, right? Okay? Now, that method, because x plus 2 and x minus 2, you guys remember what those are called? Those factors are called if they're the same exact object, but they have a sign in between them that's different. Basically meaning that when I FOIL them, the O and I's cancel out. Not inverses.
Let's start
Starts with a C.
correction. Common core. No,
What do you say? You say conjugate?
no.
You sure? Yeah, good job. They're conjugates, okay? So x plus 2, x minus 2, because they're the same terms but different signs, we call them conjugates, ultimately meaning then that when we FOIL, the B term drops out. That procedure is not as easy to see or to replicate in something like example 2, okay? We can do it, it's just not preferred because we don't recognize these as perfect squares, because they're not, okay? But if I was going to use the square root method here, what am I going to do first? Okay, you're going to add 7. Now, you said divide first, and that's fine, okay? Division and the addition here are independent of one another, so it doesn't matter if you divide everything by 3 first or move the 7 over and then divide by 3. I get x squared, what's going on, like that, x squared is equal to 7/3, right? So then take square root, which eventually, if I rationalize that, multiply by radical 3 over radical 3, I get plus or minus root 21 over 3, right? Okay. Now, if I wanted to use the conjugate technique, that's fine, but I need a difference of perfect squares here. Well, what I'm going to do first, I'm going to divide everything by 3. Get x squared minus 7/3 is equal to 0. The reason I want to do that is so that I can set up my conjugate so they both have an x in front of their factors. One's going to be plus, one's going to be minus. Now, the last one was a 4. So all we do is we take the square root of 4 and put a 2 and a 2, right? Okay, if it was x minus 9, we take the square root of 9, we put a 3 and a 3. Well, 7/3 is not a perfect square, is it? Okay, so I don't know the specific value that needs to go there, like if it was 4, I know the specific value would be 2. But I know a symbol that can go there that represents the perfect square, or it's the square root of 7/3. Can I put, wow.
No.
Can I put the square root of 7/3 right there, and the square root of 7/3 right there? Does that make sense to everybody? If I FOIL that, x times x gives me x squared. X times root 7/3 gives me x times root 7/3. And then I get negative x times root 7/3. So those will cancel, right? And if I take radical 7/3 times radical 7/3, a radical times a radical, if the radicands are the same, just gives me the radicand, right? So radical 7/3 times radical 7/3 gives me ultimately 49 ninths underneath the radical, which turns into 7/3, right? One's positive, one's negative, so it's negative 7/3. So you can do it that way. Now I've set that equal to 0, and I can solve and get x equals plus or minus root 7/3. So that's a technique that you can use, and there will be instances in calculus that you have to do that for procedures called differentiation and integration. But for all intents and purposes in algebra, doesn't the example on the left make more sense?
Yeah.
It's quicker, right? Okay. Maybe to prove that this is okay and that this works, could I start with that right there? And could I, so I break it up into two things. Like, let's just say it says x equals root 7/3. Could I subtract root 7/3 from both sides to get x minus root 7/3 equals 0? And then if I had x equals negative root 7/3, I could add 7/3 to both sides, or root 7/3 to both sides, and I'd have x plus root 7/3 equals 0. Okay, and that would generate my two factors that match. to this right here. Okay? Is that all right with everybody?
Yes.
What about the next one? What do you want to do here? What do you think the best approach would be to factor that thing? X plus 1 squared times 2 equals 4. Okay, so you want to take this 2. Let's leave the 2 there for a moment. And then you're saying rewrite this as x squared plus 2x plus 1 equals 4, right? I don't know why that thing keeps going to... I don't know what's going on. I don't know why the size of this thing keeps changing. All right, so it equals 4. Now what do I do? What do you say, Chuck? Okay, divide by 2 on each side. X squared plus 2x plus 1 equals 2, right? Subtract 2 from both sides. We get that. Now, can you think of any two numbers that multiply together give me -1, but add to give me 2? There are no such values, right? Okay. So what do I have to use then?
Non-solution.
Oh.
Oh.
Won't that work? Quadratic formula is always your default, right? Okay. So let's go ahead and do that. So it's going to give me x equals, opposite b would be -2, plus or minus. B squared would be 4, minus 4, a is 1, c is -1, all over 2a. Okay, so that discriminant is going to turn into 8. And then, is that going to turn into -2 plus or minus 2 root 2 all over 2? The only time that I can take an expression like that, because I've got a sum in the numerator and I've got a singular denominator, is if each component in the numerator has the factors that the denominator has, right? So they all have a 2 in them, so I can factor that out. And I'm left with -1 plus or minus root 2. Okay? Would you agree that took a little bit of time? Is there a quicker way? At that stage right there, can you divide by 2 to both sides? So x plus 1 squared is equal to 2, right? Now, the way that's written is that we've got an object on the left-hand side squared. Okay, I don't care if that object is a binomial like this is, or it could be a trinomial, or a 4th degree, 5th degree, whatever. Can I take the square root of that and isolate the x plus 1? I square root that, so I get x plus 1 equals plus or minus root 2. What can I do to solve for x? Subtract 1. Does that answer match that answer? Was doing it in green much quicker? Yeah, and we avoided the quadratic formula and all that simplification had to be done. And that's the idea of algebra, guys. That's why this class, you're going to see a lot of stuff that we do is the same as what you learned in Algebra 2. But now we're learning which approach is best fit for the problem that we're on. And we want to start thinking about that. We want to be, foreshadowing and think, okay, what's the next step going to lead to? More work or less work? Okay? And I told the last class, every test you have in here will be designed for you to finish within the allotted time, whether it's 1 day or 2 days or whatever, provided that you use the most efficient techniques. Okay? If you're sitting on every single quadratic equation that we come across in a test, and you're trying to use the quadratic formula for every one of them, you're not going to finish. Okay? Does that make sense? And that's kind of what, obviously we use math to kind of explain our the physics of the world and how everything's kind of tied in together. But at the same time, it's kind of a game that mathematicians have made that we try to come up with new procedures, new ideas, new processes that allow us to do old things quicker, okay, or old math quicker. Okay. So you guys remember completing the square?
Yep.
Okay. So again, some of the stuff, guys, is the purpose of doing this. Obviously, you've seen complete the square before. You've seen it in geometry. You did it in algebra 1, and you did it in algebra 2. We have to make sure that we understand how to do it because 4 weeks from now, 5 weeks from now, it's going to be kind of an intermediate process that we cannot skip over in some of the problems that we're going to do. Okay, so we've got to have that foundation. We have to understand what we're doing here. So we'll do one of these, and then we'll do the proof for the quadratic formula. All right, so if I'm completing the square, the first thing is to make sure that term, your A term, is 1, right? So every time that you complete the square, first thing, divide all terms by A. And the second thing will be move C across the equal sign. Those two steps are actually independent of one another, meaning it doesn't matter the order that you do it. If you want to divide everything by A first, and then move the 13 over, or if you want to move the 13 over and then divide everything by A, it doesn't matter. But we need to get this written as x squared minus 8x equals negative 13. Next thing you're going to do, you have your B term, square it, and add to both sides. So what's half of my B term? 4 square it, 16. Now that's always going to be a positive number, right?
Yep.
Okay, square negative, you get a positive. Square positive, you get a positive. So when we do that, then the left-hand side rewrites as a binomial squared. Okay, this, terminology-wise, we call that a perfect trinomial. And by definition, just a perfect trinomial is any trinomial that can be rewritten as a binomial squared. So this thing here is going to be rewritten like this. Now, the sign that goes in here will always be that sign right there. So in that case, it's minus. Does anybody know what goes here? Think about foiling something. Foiling this binomial so that you get your last terms to give you 16. What has to go here? Has to be 4, right? Okay. That term, that term is always your B over 2. Remember, we're taking B, which was negative 8, and dividing it by 2, gives me negative 4. And that's what that term always has to be. So that is a binomial squared, which if I FOILed that out, it would generate that. And then the right-hand side is 3. What can I do now? I want to solve for x. Square root both sides. X minus 4 plus or minus root 3. Then x is equal to 4 plus or minus root 3. So we're going to use the square root method. I don't know. I apologize for the screen wigging out there. It says use the square root method then to solve for x after step 4. So that's completing the square. Okay. Now what I want to do, you guys remember doing that?
Yeah.
Okay. If you remember like conic sections last year, there were times that you had to be able to complete the square to take a circle's equation and transform it into maybe a more obvious format. Okay. So maybe you took a standard equation and transferred it into the center radius format of a circle, so you can graph it easier. In those situations, completing the square is necessary. You cannot go around it. Okay. But if I'm just factoring an equation or factoring an expression, I can go around the completing the square process. And going around the completing the square process is the quadratic formula. If you were to take the quadratic formula and plug in a to be 1, b to be negative 8, and c to be 13, you will get exactly what we got down there. Okay? Now, in my opinion, it's going to be a little bit more work because you're going to have to take square roots of larger numbers. You got some order of operation stuff to work through, but it will always work. Okay? I want to talk about why the quadratic formula always works. So, we're doing another proof. This one I'm not going to, just to save a little bit of time. Was it hard?
Yeah, I didn't know what the hell was doing.
Heck. You're welcome. All right, so I don't want to write all the words down here, that like transitional words to get us to the proof because we're going to run out of time. But I want to prove the quadratic formula. So the first thing we're going to do is start with ax squared plus bx plus c equals 0. Okay? And what we're going to do with that, if you remember, the quadratic formula will be your default way of factoring anything, right? That right there represents the anything. That represents any polynomial, any trinomial, quadratic trinomial that I could ever come up with. Okay? Let's complete the square with it. Okay, so let's do that idea of getting my a coefficient to be 1. So how do I get my a coefficient to be 1? Divide everything by a, right? Okay, so if I divide everything by a, it's going to give me x squared plus b over a times x plus c over a equals 0, right? Okay. Now the next step was to move that to the other side, right? We'll take x squared. We're going to have to turn my computer off after we do this. Can I get that? Okay. You remember the next step we did when we complete the square? If this was 8, what do we do with that 8? Okay, so I'm going to half it. Okay, so what's another way of halving something? Instead of dividing by 2, multiply by a half, right? So take B over A, and I'm just going to do this scratch work on the side. Take B over A, multiply it by a half. That gives me B over 2A, right? So that's halving this middle term, and now we need to square it. So does that turn into B squared over 4A squared? Does that make sense? And that is what you add to both sides. B squared over 4A squared plus then B squared over 4A squared. This is then that procedure, when we did it with specific values, turn the left-hand side into a perfect trinomial. And it should be able to be rewritten as x. Now it'll be that sign there, so in this case plus, and that will be something squared. Remember what went there? If it was 8, 4 went there, right? If it would have been 12, 6 would go there. So it's always half that middle term, right? Well, wasn't this half that middle term? B over 2A? Is equal to, now I'm going to rewrite the right-hand side. I'm just going to use the commutative property. I'll flip-flop those two terms. Because now what I want to do, look at that right-hand side. That's two fractions. They're not the same denominator, so I can't merge them. Let's make them the same denominator. What do I need to multiply C over A by so that I can get a common denominator? 4A. So when I do that, the right-hand side turns into B squared over 4A squared minus, now I'm going to multiply these three terms together. I'm just going to conveniently rewrite it as 4AC. You can write it whatever you want to, any order, but 4AC I think makes sense for it. And this would be 4A squared. Left-hand side still x plus b over 2a squared. Let's take that and move it up here. The right-hand side then can be merged together as b squared minus 4ac all over 4a squared, right? Does that numerator look familiar? Yeah. The numerator right there is our discriminant, right? Okay. If this is now set up to where you have a binomial squared, and this, whatever a, b, and c are, this is one value. How do I solve for x? Square root. Square root there, square root here. So I'm going to get x plus b over 2a is equal to plus or minus Okay, now when I take a fraction and I take the square root of a fraction, can I put the numerator in its own root and the denominator in its own root? Okay. So what I'm saying then is that I should be able to do this. Right? So top turns into b squared minus 4ac underneath the square root. And this here, what's 4a squared? What kind of thing is that? It's a perfect square. Okay, so square root of 4 is 2. Square root of a squared is a. Does it give me 2a? Now solve for x. You're going to move this to the other side, right? Through subtraction. I move that to the other side through subtraction. You have now two fractions that have the same denominator, so how can you rewrite that? Merge it so that we have only one denominator, right? So do we end up getting to the point that x is equal to the opposite of b plus or minus the square root of b squared minus 4ac over 2s? Just through some algebra, right? Okay? But that's to prove to you that regardless of what you start with, A, B, and C can be anything they want to be. If you plug them into that, you will solve for x. Okay? Now, what I want to, so the idea is we went all the way through all that stuff. All that was the complete the square process, right? Okay? There will be times, like the question we did earlier, complete the square, everything was integers. But there will be times when those A, B, and C values don't provide me nice integers when I complete the square. What if my B term was odd, right? So 7 over 2, and then I square that, I get 49/4, and now I've got to go through all this algebra right here with those specific numbers of 49 and 4. And I do, common denominators, and I got to do all that garbage to simplify, where if I just jump to the opposite B plus or minus square root of B squared minus 4ac over 2a, I skip all over that work. Does that make sense? Okay? That's the proof of why that works. Okay. The assignment in WebAssign, keep working on that. It will not be due Monday. I'm probably not going to get to change the due date until Monday. So don't worry about that. Whatever I tell you guys in class, even if the date doesn't change right away, what I told you in class will always hold precedent over what the due date on WebAssign says. So it's not going to be due on Monday, but you can continue to work through that, maybe do a handful of them, that model, what we talked about today.